Distribution of the Antarctic fish Pseudochenecthes georgianus Norman, 1939 in the Atlantic sector of Antarctic. The Changes of Otolith Shape, a book of stories about the nature of the distribution of fish georgianus and not only for fish. Terrestrial observations of separate geographical and vertical living on different age groups and species of fish suggest that differences in otolith shape among them became from difference in their environment conditions. For example, the decrease of the otolith length and increase of the otolith height as water temperature is dropping.
Age groups of Georgianus separated in time scale confirm geographical divide of otolith mass frequency as separate age groups on Antarctic islands. 2-aged fish at Palmer Archipelago in February, 3-aged at King George in March, and 4 years and more aged fish at South Orkney in December. This same as for age groups in length frequency geographically divided on separated Antarctic islands. Georgianus of the younger age groups prefer the western part of the Atlantic Antarctic, but the older age group east-north part. Age group is identified by otolith shape, which, indicating the different habitats, development stages and strategies of life, type of swimming.
Water temperature determines distribution of Antarctic fish. A stratus from larvae to fish of 2-year-old has weaker activity of AFGP proteins than adult fish. Adult fish at the age of 4.5 years have large activity of AFGP. That is accompanied with 4 times increase of their swimming possibility and diet change to eating fish. It seems to be the role, because also concentration of protein activity AFGP for the high Antarctic fish depends on the stage of development of the fish, synchronizing with space system of water temperature and food. Warman, 1996. Concentration. The activity of the AFGP protein in the white-blooded fish is increasing in colder water in the direction to the pole, and with the depth. Bialik, 2011. Geographic age groups in otolith shape, we can find being in well agreement with their food size of krill migrating, drifting and growing with currents to the east. Second age group were captured Palmer Archipelago among juvenile krill. Adult fish, age 4 and above, were caught at Orkney Island, among larger adult krill. Thus on the north, east of Shetland Islands large adults Georgianus, of age 4 and above from King George to South Orkney have to withstand stronger surface currents and whirls. In opposite south, west side of Shetland's larvae and small fish have protective environment on their shelves extended by ice edge zone to the South Orkney. The ice edge connecting King George, Elephant with South Orkney, were located over mountains that combine undersea above islands. The Astratus and other larvae were near ice edge. There is synchronization of the size of the fish, of its ability to swim to the size of the food. The Antarctic circumpolar current, the Weddell-Scotia confluence, creates in Shetland a system of currents, whirls and countercurrents, where Georgianus lives and to which it has to have a strong adaptation to survive. This system together with ice edge zone inhabited by krill and fish larvae have great potential for migration of fish even for shelf species. Such conditions are often extend to South Georgia. Although it is a small area, shelf of South Georgia were also separated geographically on age group of Georgianus. In summary, the smallest fish were on the western side far from the shores. They were moved by currents to the west. They stay here longer as age group of 2. On opposition, large and older fish that are better swimmers were at northeast feeding on large krill accumulated by whirls. Permanent turbulent flows causing local accumulation of large krill. Such an arrangement is not accidental because is repeated year after year. Georginus live in currents to break krill. Worse, swimming larvae were protected by coastal bays, reducing the strength of currents and forming countercurrents. Postlarvae are flowing away from the shore in a current flowing around the island and congregate in confluence of two currents into one age group in the west of the island. The small fish from age group of 1 there were only at deeper waters 250 to 500 meters. This suggests also the vertical separation of the young age groups from the older. Separated geographically, age groups were differentiated by the ability to swim in the currents and eddies needed to get food in them. This ability is managed by otolith shape. Y. Hydrodynamic resistance, RAH, is the smallest for flowing shape and is equal to 1. Thanks to habit, fish mastered ocean space. Success in obtaining food provides higher speed of swimming. This has also a reference to the otoliths provide in swimming the balance and precision. The flattened shape of the otoliths poses little resistance in endolymph and increases the perception of positions in fast swimming. The shape of the otoliths is the indicator of the lifestyle and character of habitat. Otoliths have changes of shape during the ontogeny as the speed of fish swimming increase. After hatching, otolith's shape becomes more flattened from 2 to even 3 times. Further flattening of otoliths runs from postlarvae to fish of 1 age group by second primordium. The increase in the otolith flattening by second primordium increased the perception of balance during vertical migration. Large dorsal area indicated large vertical movements has high growth rate. It shows faster growth of otolith height than otolith length. For 30 centimeters Georginus above 2 age group, high growth of anterior colliculum give larger sensitivity of body balance in swimming forward need in surface currents. The otolith shape of Georginus is changing by the life stages. How do we know that the shape of otolith indicates the speed of swimming? From comparison, faster species have them more flat. The height of otoliths inform about vertical stability needed for vertical migrations and for lifting with currents. Long otoliths of mackerel are sensitive on changes during swimming in the horizontal direction. The shape of otolith is changing among species of fish of different depth of living. Length of otolith of fish Macarus carinatus is large. They are not very fast swimmers, so that is the impact of higher hydrostatic pressure of about 1,200 meters of the column water. Transverse section across otolith carinatus is similar to Chanichthyridae, but proportions are inversed. Otolith shape differentiates the pattern of high-energy swimming of mackerel with body waves. Pulsed swimming in squids creates twins hemispheres in otolith shape. Low-energy swimming of icefish Chanichthyridae by using large pectoral fins, floating fish in the depths. The accuracy of vertical movements are measured better by higher otolith. Lifting strategy. The use of currents and the uplift force of fins. High laterally flattened body takes over the energy of sea current. An asymmetrical shape creates differential pressure on opposite surfaces, and thus the driving force to forward. Factors increasing the force acting on the body. Growing of lateral surface of fish body. More smoothed surface of the body, larger sensitivity and skin elasticity, the fins. Body shape is an indicator of the shape of otolith. Georginus has body height greater than the gunari and astratus. Otoliths of Georginus like its body are high. Larger flattened otolith indicates a faster swimmer. Georginus, otolith little flattened, small range of the currents. Astratus has body less high, but its fins are longer. Otolith length of Astratus is longer than the height. Astratus, otolith more flattened, average range of occurrence. Gunari the most slender body with the big fins, otolith height is lesser than otolith length. Otolith most flattened, the greatest range of occurrence. Chanichthyidae. They have an increase in activity and production of antifreeze proteins. All Chanichthyidae have lost hemoglobin, but each species has a different compensation of reduced oxygen transport to fulfill a different environment. At first, larger body. Bottom lifestyle of Chanichthyidae, the reduction of the axial muscles, the large volume of blood, a reduction of ossification, to reduction in body weight. Pelagic life Gunari of Chanichthyidae. Slender body shape, more capillaries. Larger capillaries and large spaces with blood. No reduction in axial muscles, consuming less energy. Semi-pelagic lifestyle of Chanichthyidae. The shape more compact, producing loss of heat through the smaller surface of the body. The heart of Georginus has myoglobin, which increases the amount of oxygen to the heart. Different otoliths among icefish could be confirmed in their occurrence and interspecies ratio. Georginus occurred more numerous on the northern and eastern shelf of Georgia Island, while Astratus on the west side. Georginus swims in warmer waters. Astratus swims in colder waters, shallower. Gunaris has a more wide, pelagic life. Shallow waters are warmer on the northeast. The dominant age group of one of Georginus, whose otolith's shape is more oval, is spreading on the shelf to the west to cooler water, and Astratus now colonize its eastern shelf in the absence of its predator. Georginus now dominates as 3 age group of mature fish in the northeast, in a warmer area of larger current turbulences accumulating krill. The change of otolith shape from the ball in to elongated can be traced in the evolution of capabilities and speed of swimming of animals on successive organization level of the animal kingdom. Radial symmetry have spherical statoliths in the edges around of body. The changes work on body shape and statolith localizations. Ctenophora, changing body to bilateral symmetry and statolith localization in a front to head. Statocysts at 2 sides of the brain. Their shape and growth rate varies according to the needs of the increasing swimming speed. The abandonment of bilateral symmetry related to free lifestyle causes the loss of statocyst. Statocysts only if they have a bilateral symmetry as a form more useful in the free mode of life. Deuterostomes repeated the centralization of the sense of balance. 2 statocysts, each developing a labyrinth in bilaterians. No significant changes in labyrinth of terrestrial vertebrates.